Hi, this is Jeff Coronado on behalf of JCSC, and this is a session in Bridging the Gap. For those of you who might be unfamiliar with our sessions of Bridging the Gap, this gives you a little bit of an idea of what we are doing here. But you can certainly take a look at our introduction on the JCSC LLC Bridging YouTube channel. In the introduction, I give you a better idea of what it is that we're doing here. So by all means, take a look at the introduction. But with that said, I'm going to jump into this particular session. And in this session, the title of the session is WW12-2. So it's the second in a sequence of sessions related to WW12. And what we're going to cover in this particular session is Rafter Supports. Okay, so this is type 5 framing, Rafter Supports. And the question is, how do we model the supports for the rafter in this connection? So let's move on and take a look here. So we've already visited the detail. I believe that was covered in session 1 of the sequence of this sequence of sessions. But we've got, use a spotlight here. So we've got this rafter, we've got a ridge board here. We've got a rafter coming down here. So we've got pitched rafters, right? And then we've got a beam that supports the rafter at the lower end. I think, well, it's not entirely clear whether this would be symmetrical. Probably doesn't really matter what's going on the left side, because the reality is we're not focused on this rafter that's highlighted in red. We're focused on the rafter in yellow, right? Okay. Modeling supports is somewhat interactive. The supports are modeled based on the real conditions of how the connection is built. So here, yeah, it's always a little tricky, right? Because if you don't have the experience yet to know maybe how these connections are typically made, you're going to be a little bit at a loss. So hopefully we can help you out here a little bit. Typically, what you would want to do is start off with making connections in a standard way, in a conventional way, right? And then based on that conventional way, that's how you're going to then model it, right? As an engineer, you're going to model it. And if the connection, if for some reason something doesn't work out, your stresses don't check out, your limitations, limit states don't check out, then you might need to alter how the connection is made, so that in turn you can alter how you're modeling it, right? Because perhaps by modeling it slightly different, you will get your limit states to check out. Okay, so let's look at a typical way of connecting this rafter, right, to this this ridge board. And the way that is typically going to be done is really with nothing more than perhaps a couple of nails, just a couple of nails. They might even be toenails. In fact, they probably are toenails, which means that if we look this way, if we cut a section and look that way, right, what we're going to see is our ridge board, and then our rafters kind of framing into that ridge board. And by toenails, what we mean is the framer, the carpenter, is going to get a nail and drive it into the side of the rafter, and embed it into the ridge board. Okay, if we look at a top view of this, then what we would end up with is your ridge board is going to look like this. Your rafters are going to frame in, right, to that ridge board. Your rafter will be framing in on the other side. Remember, this is a plan view, right? And then your your nails, your toenails, are going to be driven at an angle through the rafter into the ridge board. Okay, this is the head of the nail out here, right? This is the head of the nail. So you're driving a nail at an angle through the rafter and into the ridge board. Okay, so with that in mind, how are we going to model the left support of this rafter? Have we provided resistance for the rafter in the vertical direction? I would say yes. I would say yes, right? Those nails are going to keep the rafter from sliding up and down, okay? Have we prevented displacement of the rafter in the horizontal direction? You know what? I just took another look at this, and I'm gonna backtrack on that. I'm gonna say no. I'm gonna say that I mean, yes, we do have vertical resistance for this rafter, but horizontally, let's think about this. Horizontally, if I were to push on this rafter from right to left, do I have resistance? I would say yes, right? I would say that the opposing rafter can push back. And then of course, it almost kind of depends on how we're connecting the rafter on the left side and maybe how we're connecting it at the bottom end. But I think for now, I think it's safe to say, we can say, yes, I am resisting motion to the left of this rafter, but am I resisting motion to the right? Right? You know what, let me do an arrow on that. Am I resisting motion to the right? And I would say if the only thing that's connecting this rafter to the ridge board is these toenails, and I try to pull on this rafter, those nails are just going to pull out of that ridge board, right? That's not much resistance. That's not much resistance. So in reality, I think we can provide resistance for this rafter in a vertical direction, but not in a horizontal direction. What about moment? Are we able to resist moment? Are we able to fix? Do we have fixity between the ridge board and the rafter? And there, I would certainly say no, right? If I were to come in here and let's say try to lift up, try to spin this rafter about the ridge board, about here, and I grab the rafter and I pull it and I spin it, would those couple toenails keep the geometry, keep the angle, keep the geometry between the ridge board and the rafter intact? I would say no, right? The rafter, again, the rafter is just going to pull away from the ridge board if the only thing that's connecting it is those couple toenails. So I would say no, we can't resist moment with this connection. Therefore, we don't have fixity. So now all we have on the left side of the rafter is the resistance, is the vertical resistance, right? So let me undo, I'm sorry, not undo, let me erase this, and this, and this. Let me erase all of this, okay? And this is what we're left with. So really, it's a roller, right? On the left side, I've got a roller, or you have a roller. The only resistance that this connection is providing for this rafter is displacement in the vertical direction. Okay, now by extension, let's do similar thinking on the right side of the rafter. Okay, let's start off with horizontal displacement. Am I resisting horizontal displacement of this rafter? Again, we can't really see the connection here, but what would be standard is to provide, again, a couple toenails, so driven into the rafter at an angle, and then going sideways into the beam, into this larger beam down here, right? So with that in mind, is this connection providing resistance to a displacement to the right or a displacement to the left? And I would say yes, right? Now let's look at vertical displacement. Is this connection providing vertical displacement for the rafter? Okay, let me erase this and this and this and this. So do we have vertical resistance here? Well, I think it's fair to say the rafter would not be able to go down because it would push, it's bearing on this beam, right? So it's not going to be able to go down. Is it able to go up? Tricky question. Is it able to go up? I don't know to what extent you can see this connector here, but that connector is what's critical. That is what is being added in this connection above and beyond the toenails, which would be pretty standard for a contractor, for a framer to place those toenails on the rafter to beam connection. We've got this clip. This is a hurricane clip, and the hurricane clip is there to prevent uplift. It's there to provide that resistance so that if the rafter does try to pull up, it's connected to this beam, and in turn it will pull up on the beam. What does that mean for us modeling this? That we've got resistance in the vertical direction and we've got resistance in the horizontal direction. Now, if I try to spin this rafter about the beam, right? So I fix it here, I hold it here, and I try to spin it about the beam. Am I going to be able to spin it? Yeah, pretty much so, right? Very little here to keep this geometry intact, right? Very little to keep the angle between the rafter and the beam intact. Yes, that beam with those couple toenails and even this hurricane clip, I'm going to be able to lift it and spin it about this point. So no, I don't have moment resistance. I don't have fixity at that point. So what we have is resistance in the vertical direction and resistance in the horizontal direction. I do not have fixity. So what that tells me is that I have, and for lack of a better model, I have a pin connection at the lower support. Okay, so I'm left with a pin connection. Let me redo that then. I'm left with a pin connection at the bottom side of the rafter and a roller connection at the top side of the rafter. A simply supported element with a roller at the top and a pin at the bottom. Okay, so I think with that, we've covered how we would look at this particular rafter, how we would model the support, what's the thinking that goes into selecting the idealized support conditions from an engineering point of view. Let me clear this and see what else do we have here. That's basically it. That concludes WW12-2. That's the rafter support for this connection. Again, please take a look at the introduction to get a sense of what we're doing with the Bridging the Gap sessions. By all means, search our channel for other WW12 sessions, which will then be related to this particular detail. We will cover other aspects of the detail, such as how to size the elements, how to calculate forces on the connections that are involved. If you enjoyed this, if this was helpful to you, appreciate you giving us a thumbs up. Also feel free, or I guess not even feel free, right? Appreciate if you hover over the JCSC logo, which is on the lower right-hand side. You can click on that, and that way you can subscribe to our channel and stay tuned to other Bridging the Gap sessions. Okay, real good. Thank you.